welcome to our session, Quantum Computing 101, What Government Agencies Need to Know. Hi, by way of introduction, my name is Emily Jarvis, and I'm the Senior Manager for Events here at GovLoop, and today I also get to be your moderator, so thanks so much for joining me. And a special shout out to our sponsors at Dell Technology and FCN for helping us put on this session today. So, quantum computing might sound like something out of a science fiction movie, but its potential to transform government operations is very real. And from solving complex problems to powering next generation simulations, quantum technologies are poised to reshape how agencies think about data, security, and innovation. And whether you're just hearing about quantum or looking to understand its practical applications, this session will break down the basics and explore what it means for the future of public service. But before we get to all of that, I do have a few housekeeping items to go over. First things first, we have some great resources available for you on the console under the resources button. So make sure you check out those additional learning opportunities. That's also where you can learn a little bit more about our speakers. So make sure you check those out. If you need access to the closed captioning feature, just look for that show captions icon along the bottom right-hand side of the panel, and that's where you'll find that added accessibility. Now, we hope you don't have any technical difficulties, but they can and do happen. And if they do, send us a message to that Q&A tab, and one of my GovLoop's colleagues will get you all sorted out. You can also use that same tab to submit questions to our speakers, and we want your questions, so don't you dare be shy. Put your questions in early and often. You can also engage with your fellow attendees using that chat button as well. Finally, we are recording this training, so check your inboxes tomorrow because we'll email you a link so you can watch the entire session on demand. All right, with all of that housekeeping out of the way, let me introduce you to our speakers. Joining us, we have Mohammed Shabli, who is the doctoral researcher for the University of California, Riverside. We also have Paul Stimmers, who's a partner at Holland and Knight and an executive director of the Quantum Industry Coalition. Thank you both so much for being with us today. And to better understand how quantum really works, my colleague and quantum expert, John Monroe, sat down with each of our speakers to get their perspective. Here are those conversations.
Hello, everyone. My name's John Monroe, and I'm the Director of Content here at GovLoop. And we are here to talk about all things quantum. And for that, we are joined by Paul Stimmers. Paul is the Executive Director of the Quantum Industry Coalition. He is also a partner at Holland and Knight. Thanks for being here, Paul.
Thank you for having me. Delighted to talk with you.
All right, so lay the groundwork for me. Let's start with the basics. What is quantum computing and how is it different from classical computing, the computing that we're all used to?
So quantum computing uses the unique properties of atoms and subatomic particles that don't have any corollary in what we think of as the physical world at our scale. So for example, you can look at an atom or an ion or another subatomic particle and not have any idea whether it will be doing one thing or another until you actually measure it. And you can cause two or more such particles to be entangled, such that when something happens to one of them, it also happens to another, even across vast distances. And you can use these properties to do math, and the kinds of math that you can do with quantum computers, or will be able to do, are the kinds of math that get much, much more complex when you add additional variables. So we classical computers are good at the kinds of problems that get somewhat more complex when you add more variables. But when each variable you add doubles the complexity of the problem, you run out of classical computing resources very quickly. And that's where quantum computing can come in And a quantum computer can consider all sorts of various different kinds of information outcomes at once, all the answers, if you will, at once, such that if you have roughly 100 fully functioning quantum bits, and classical computers have a tremendous number of bits, but if you have 100 quantum bits that actually work, you can hold within them roughly the number of atoms in the known universe
Mhm.
worth of information, which sounds like a lot, and it is. But then the quantum computer is able to resolve that into the answer that you're asking it for by essentially just finding the lowest energy state within that entire realm of possibilities very quickly. And so sometimes people talk about a quantum computer being vastly faster than a classical computer. They'll say, "Oh, we can do something in a few minutes that would take septillions of years for a." Well, that's not a meaningful difference to my mind. What you're really saying is we have an entirely different tool,
Mm.
right? I can build a dam faster with, dam building tools than I can with a slice of American cheese, right? It's not the same thing. So quantum computers are going to be a different kind of tool for a different kind of problem, the kind of problem that gets very complex when you add variables, and they're going to complement the the current set of tools that we use for other problems. Classical computers are going to continue to be very good for all the things that classical computers are very good at.
So, what are examples of what quantum is likely to do very well that right now, you know, classical computers just may not be up for?
Well, the scariest one,
Yeah, let's go there. Why not?
the scariest one is that quantum computers will be very good at decrypting
Yes.
standard RSA encryption, right? So our current encryption relies on the idea that it is very easy to take two extremely large numbers, prime numbers, and multiply them together and get a result. That's pretty straightforward. It's very difficult to take the resulting extremely large number and figure out which two primes created it. And the way I like to think of it is it's very easy to dump salt and pepper together. Very difficult to get them back apart. You get handed a pile of salt and pepper and some tweezers, and you're going to be there for a while. That's what it's like for a classical computer, and that's the fundamental basis of our digital security right now. Um, a quantum computer, though, because it has a different way of approaching the problem, a quantum computer can find those factors instantaneously. And the way I like to think of it is you've got that pile of salt and pepper, and you just dump water on it.
Mm.
And it's a different tool than the tweezers, and the result is instantaneous. And so that's how that is going to be one immediate application of sufficiently powerful quantum computers. And we know that it is because quite some time ago, an algorithm was proposed for a quantum computer that still doesn't exist. That if the computer were powerful enough, it would be able to run it and decrypt encryption. It's called Shor's algorithm, named for Peter Shor. Uh, and we know that it'll work. We're just waiting for a computer powerful enough to run it.
So it's almost like there's an arms race here. So we got the algorithm out there that can do it. So people really, so this one big concern right now is organizations need to get to kind of quantum proof encryption before the technology is there to crack the old algorithms.
Oh, it's worse than that.
Oh, good, good.
So that's absolutely true. We need generally referred to as post-quantum encryption, which, by the way, doesn't itself require quantum computers, right?
Hmm.
Post-quantum encryption is just a different kind of math that's also hard for quantum computers. So we need post-quantum encryption not only before we get the quantum computer, but our adversaries and thieves and whatnot are stealing encrypted data right now, data that we're storing in encrypted form. They're stealing it, and they're just hoping that it will still be interesting when they get a quantum computer capable of running Shor's algorithm. So to the extent that your data right now is going to be interesting then, you already need to have it encrypted with post-quantum encryption.
Mm,
And so we're in a position right now where we're just trying to limit the damage by getting post-quantum encryption done. And NIST, the National Institutes of Standards and Technology, have proposed and sort of promulgated a set of standards that that companies and data owners can use to do this post-quantum encryption. If you encrypt it now with post-quantum encryption, you've limited the damage to whatever the bad guys already have.
right.
But if you think that your data is still going to be interesting 2 years from now, and you think a quantum computer is 3 years out, then you have a year. If you're right, you have a year to do post-quantum encryption. Most of our data is going to be interesting much longer than that,
Right.
and our timelines are not that long.
Well, that's encouraging. All right. So, all right.
But
Well, let's
but
think.
there is a solution. We can do it. It just needs to be done. It's like Y2K. It's a big push, but
Yeah.
it can be done.
Do you feel like that urgency is recognized? I know NIST is obviously, pushing this and, raising the alarms. Do you feel like that people understand kind of the timelines that we're talking about?
I think many IT professionals do.
Yeah.
But IT professionals are sometimes like the mythical Cassandra. They are cursed with the ability to see the future, and then nobody believes them. And so our job as people who are advocates and who sort of see what's coming down the pipe is to help make sure that people are aware that this is the vulnerability that they have and that there is a way to address it.
All right. So let's talk about kind of the impact in other areas. Logistics. That's something we hear about. What are we talking about here?
So again, logistics is an area where the more variables you have, the more complex it gets very, very quickly. One of the sort of classical problems in this space is called the traveling salesman problem, and it's a very simple looking thing where you've just got a series of cities and you're trying to find the shortest route for the salesman to travel. That turns out to be incredibly hard,
Hmm,
and much, much, much harder than it looks. And that's a set of problems, optimization problems, that exist throughout the field of logistics. And quantum computing is able to handle that much more effectively than classical computing, to the point where if you're, say, the US Postal Service, and you want to know exactly how your routes should be run on any given day, um, you can use a quantum computer to figure that out. Where this gets really interesting is logistics. I can't sugarcoat it. Logistics is really boring to most people.
right. Yeah.
Um, and that's why every single war we fight, we have to relearn the fact that logistics is what wins wars. It's
Yeah.
not the fancy platforms. It's the ability to get things where you need when you need them. And so the ability to do better logistics is a national security capability.
Got it. Actually, so let me bounce something off you. I think I heard this once. I want to know if this is accurate. Someone once explained to me, if you think about, say, a maze, solving a maze, um, that, so if you use a classical computer, it's going to try one route after another
Mhm. Yeah,
till, it gets there. But with quantum, because of those quantum properties, it's almost like it's trying all the routes at once, and then, like you said, kind of resolving. Is that an accurate picture?
that's right. Yeah, it's there. I will say there are no accurate pictures in quantum because none of it is, but it is correct. Um, that essentially a quantum computer will will relax into the maze, and the most relaxed aspect of it is the path. And that's, it's weird to say, it's weird to hear, but that's basically what's happening, is that the the essentially, when you think about when you think about dropping pebbles onto a pond, and they cause all these ripples, and some places the ripples intersect and get higher, and some places the ripples, a trough and a peak will intersect, and they'll cancel out, like noise canceling headphones. That's the way this can be thought of, is that, and along the path, all of the waves are intersecting and canceling out, and you can see the path. The computer can
Right.
essentially feel feel the path, uh, and it just happens again more or less instantaneously.
So suddenly I'm thinking about use the force, Luke. It's like, yeah, it's kind of like a it's a quantum analogy.
A little bit, yeah.
So, if I a quick aside, it seems to me that one of the challenges with quantum right now is because it's so hard to talk about. I remember I was interviewing this physicist and he was trying to explain quantum to me and he said, there's I can explain to a point, but at a certain point you need a PhD, to really understand what we're talking about. It seems like there really is this kind of steep learning curve that, organizational leaders have to eventually are going to have to kind of get over.
Well, I mean, we like to impress ourselves with how hard quantum is, but the fact is, we don't really need to know exactly
Hmm.
how all of this works. Just as I don't know how my smartphone works.
Right.
Like, how does the touch screen on your smartphone work? Well, I think there's some sort of electromagnetic something with my finger. I don't know, but I know why it works basically, and I know what to do with it,
Yeah,
right? I know what its capabilities are, I know what its limitations are, and that's what we need executives to understand. We need them to understand that there's a new capability coming, and that it will unlock the ability to do things that we haven't been able to do before.
excellent. So one other area I'd like to get your thoughts on, and that's data analysis, because right now, government agencies are so focused on that data. How does quantum begin to change the dynamics here?
Mhm. So, a couple of things. First of all, obviously, the amount of data that is being generated all the time is staggering. And what I think we're going to see is that there will be an interaction between quantum and AI.
Mhm.
Uh, and AI is going to be crunching a tremendous amount of data. But what the combination of quantum capabilities and AI is going to bring is an ability to sort of shoot through that data much quicker and find sort of what's relevant and what the patterns are, and use it much more effectively and efficiently. Um, by the way, we have supercomputers that require just tremendous amounts of power, and data
Yeah.
centers that require tremendous amounts of power, and quantum computers that are going to be running on wall sockets.
Mm,
And so the power needs uh, for quantum computing can be quite a bit lower than some of our most advanced supercomputers, and that can be one of the keys to unlocking sort of or one of the ways through one of the big bottlenecks that we're facing in terms of energy availability. So quantum is going to be part of the solution for a lot of these federal agencies who are trying to navigate the sea of data that they have,
yeah.
use less data to inform any given decision because it's cheaper from an energy and time perspective. And it'll be interesting to see exactly how it works out, but that's some of the potential that we see.
So, okay, so we there are areas clearly where quantum isn't has an advantage. There are areas where classical computing is perfectly fine. One thing I've been hearing is that there's a hybrid model here. Can you talk about what that might look like?
Sure. And I just want to take a moment to say you're absolutely right. classical computers will continue to do almost everything. There's nothing that a classical computer is doing really well right now that a quantum computer is going to displace.
So
Uh,
quantum is going to like speed up spell check,
Right.
that's not really necessary.
Yeah, and you're not going to be wearing a quantum computer anytime soon, and your car is not going to have one. But um, it just opens up this new set of problems. What a hybrid quantum and classical computer can do is really use the best of both worlds. And it can use the classical computer to set up the quantum essentially to create the question, create the problem for the quantum computer to solve. Quantum computer solves its part, that gets fed back into the classical side, and it just speeds things up. At the end of at the end of the day, what you're going to see, I think, is users are not going to think, oh, I have a classical problem, or I have a quantum problem, or I have a hybrid problem. They're just going to say, I have a problem.
Hmm.
And some combination of resources is going to end up solving that problem for them. And that's not going to be something that they particularly pay attention to. And
Got
just as now, when I'm on my computer at home, I don't care if it's the GPU or the CPU that's solving the
it.
problem. It's I just am playing my computer game, and all of that is happening in the background.
So, so we've talked about some different areas of impact. Are there any kind of use cases now for government agencies that they ought to be thinking about?
So one of the things that the Quantum Industry Coalition has been doing as we try to reauthorize the National Quantum Initiative Act this year is to talk about precisely that. How do we help federal agencies think about how they could be helped by quantum computing? And we've talked about the basic use cases, or their optimization related cases in the early stages, and some other things. By the way, quantum computing is likely to be extremely helpful for drug research.
Hmm.
Much of the work that goes on in clinical trials can go on inside a quantum computer because it can effectively model the quantum system that is a molecule. Uh, so these kinds of questions are mostly questions that our federal agencies have sort of set to the side as not solvable right now. And so part of what we want to do is have a mechanism within the National Quantum Initiative where agencies are encouraged to look through those insoluble problems one more time and say,
Mhm.
okay, now that we have this new tool, can we do something here? And not just the ones you might expect, not just NIH or the Department of War or the Department of Energy, but heck, let's look at the Forest Service.
Hmm.
You've got national, lands management issues. Maybe we can use a quantum computer there. Um, there's a lot of different ways that federal agencies may be able to meet their mission. Obviously, the air traffic control opportunities are significant. The Department of Transportation more broadly has a number of things. There's plenty of places where we can look for these opportunities. And then the second question is, okay, now that I know that there's something that I can do to meet my mission with quantum computing, how do I do that?
Hmm.
And so helping agencies understand how they can buy quantum computing time or buy a quantum computer if that's their need. That's the next step to what we call the quantum on-ramp for federal agencies.
So, I mean, is one possible model there that there could be quantum providers that basically provide services through the cloud? I mean, are we talking about quantum software as a service kind of thing? What
Well,
might it look like?
yeah, already there are several quantum cloud providers, and you can hop on right now and program a quantum computer and get a result. And that's pretty well developed already, but still in its infancy. And I expect that we'll see a lot more of that service model as the computers mature.
So, crystal ball time. When does this become real? As in, where there's a commercial market here where, say, government agencies can procure services. What timeline are we looking at?
So government agencies already can procure services. They're still, I mean, extremely advanced from a human endeavor perspective, but still rudimentary as far as quantum computing is concerned. But they're rapidly improving, and the roadmaps that we're seeing from various different quantum computing companies and using various different architectures for quantum computing, because there's still, we haven't settled on sort of the transistor yet. We haven't even settled on a vacuum tube yet. Where there are still big questions about fundamental architecture for quantum computing, and those may persist for a long time. But we're starting to see across those various architectures the idea that in around 2028, we will probably start to see what we call quantum advantage, which is a point at which it starts making sense economically and from a result perspective to use quantum computers instead of classical computers. Not that you couldn't use classical computers, but it just makes more sense to use quantum computers. That's different from another point called quantum supremacy, which is the point where you're doing things on a quantum computer that can't be done
Mhm.
under any realistic circumstances on a classical computer. And that's a little further off. But quantum advantage is something that is virtually speaking just around the corner.
Excellent. All right. So I'm a government official. I've heard this conversation. What can I start doing? What can my agency start doing now to get ready for this kind of quantum landscape?
So number one, secure your data with post-quantum encryption. Number two, talk to your team about what their insoluble problems are, and what problems are just too insanely complex to worry about solving with a computer. And then three, talk to the Office of Science and Technology Policy at the White House, talk to the Office of Management and Budget about how you can get the resources you need to make sure that you can solve those.
Okay, great. Well, Paul, thank you so much. Really appreciate your insights here today.
Thank you, John. It's been a pleasure.
Okay, so now we want to dig a little deeper into what's happening with quantum computing and what needs to happen for this to kind of get to commercial viability. And for that, we are joined by Mohammed Shaubi. Mohammed is a doctoral candidate in the physics department at the University of California, Riverside. Mohammed, thanks so much for being here.
Well, thank you for having me. Glad to be here. Um, so yeah.
All right, well, I really look forward to hearing kind of what you've been working on, but first, lay the groundwork for me. So, what do you see as sort of the state of quantum computing at this point?
Okay. So by the state of quantum computer, we might mean what's the state of like the devices themselves, the technology, but also the state of the market, like the
Yeah.
scene itself. So let me answer the first part first. Is like who's involved. So nationally, you have a lot of national laboratories, you have a lot of universities, you have a lot of startups and tech giants that are putting efforts in a healthy competition, I would say, for the US. And on the other side, you have the global competition for sure. So yeah, so that's the stage is like who is currently pursuing quantum computer because that is kind of useful in maybe answering further questions to like it's helpful to know who's involved. So as for the devices themselves, we are in an era that we call NISQ. It's like noisy intermediate scale quantum devices. So noisy intermediate scale quantum devices. This is what we have right now. So um, we have devices that are not small, they are intermediate as the name suggests, but they are noisy in terms of like the how precise or how reliable is that computation. And even though at this scale, like there is like a lot of useful, maybe not economically viable yet, but useful demonstrations that have been done. Um, so that's kind of like I think that lays the ground to begin with. Yeah.
Yeah, so let's start talking about some of those challenges. You mentioned noise for one, but what are some of the main issues that really need to be addressed to start getting to that, moving towards that broad commercial use?
So I am kind of referencing a study here and like having it at the back of my mind. It's an amazing read that I have been recently involved in. So you can like we have the NISC as I mentioned, and on the other side you have the FASQ or FASQ is like fault tolerant application scale quantum devices. And so between these two, like there is a gap that and this gap we need to cross that bridge to to reach or like to yeah to arrive from here to here. And so there are like too many or like it's multidimensional like the gap is from different aspects. So one thing is hardware. We need to keep getting better in hardware um in like too many things and think about like what you use for like regular computing. It's the chips themselves, the memory, storage, networking, connecting devices together. So each of these needs to have its own hardware infrastructure improved by significant amount over the years. So that is one thing. The second thing is on the algorithmic scale, which is what can we do, or like what is the exact magnitude or reach of this quantum advantage, as some people may call it. And the honest answer here is that we know it's there. Like there are experiments that have verified the power and the potential of quantum computer, but quantifying it exactly or predicting what can be done exactly with quantum computer is an active field of study itself. Um, and yet, like maybe knowing what they are capable of is in itself like advantageous, is in itself a pursuit that might reveal too many interesting things. So algorithmically, we need to we need to push that front as much as we can. Um, well, and on one other side is like the ecosystem itself is like to have what we call like a quantum ready. So on the algorithms, we need to have like a quantum ready applications, but also on the security front,
Mm,
the workforce front. So you
mhm.
need to get all of these. So we need like the policies, standards. So all of these need to kind of like be pushed simultaneously. Yeah, like in the next few years, I would say.
And it seems like I know the federal government is helping with some of that, How does this get coordinated? I mean, how does this sort of happen in a way that gets people moving in the same direction, or is that even how important is that?
Well, maybe some of your audience might know better about that, like policy. So I mean, recently the Department of Defense, just like the Department of Energy, I think, they just renewed like its funding for quantum like $625 million, I guess. And I would say like this is like it's a very well coordinated effort between experts in the government, in the national laboratories, and like giants in the industries, or like senior scientists that like have their voices and their voices are heard and addressed properly. So I would say, I mean, it's a very optimistic about how the government is taking this seriously and is trying to be supportive as much as possible. So yeah, like how exactly it is coordinated, I'm not the guy to ask for that.
Fair enough. Fair enough. All right. So talk about the work that you're doing. Kind of what are you focused on and why is that important?
Okay, so what I am doing is quantum error correction. So I am a quantum error correction scientist, and or an architecture, modular architecture. So these two like both two to quantum error correction is kind of key element in getting these bigger devices kind of like working with the precision that is necessary for actually achieving something useful economically, scientifically, and so forth. And the other one is modular architecture. They are tightly related. Basically, you need to like just like we do with like classical computers, you need to be able to stitch these computers together in nodes within like the same place and also across places within cities to have like secure communication channel. So modular architecture is key to any future development of the field. And these two, I'm juggling these two basically.
So how do you where do you see yourself kind of making progress? Do you feel like that you're able to make progress now? There's still a lot of work to be done. What's your kind of sense of the state of your field?
Yeah, well, personally, I got lucky working with like my professor. He's like Leonid Priodko at the University of California, Riverside, and together, I mean, I was able to have some like tangible results. It's a tiny, teeny little push, but it's a meaningful push in
Yeah.
the right direction. And I just hope and aspire to keep doing that. Me and like thousands of course, like peers that are like extremely talented, and yeah, together we could really put this work. Like together, people at my age, at my level, along with like the seniors that people we learn from. So yeah, this is how science is being. I'm learning myself. I'm still learning about like how this wonderful like process of doing science, especially here in the USA, it's moving. It's pretty amazing.
That's excellent. All right, well, yeah, so let's talk about that. So, how do you see the field of quantum computing evolving over the next several years? What does it look like from where you sit?
Okay, so forecasting is not really
Yeah,
my
get out your
my
crystal ball. Get out your crystal ball. You have one of those, I'm sure.
Okay, amazing. So let's say that so again, it's like that bridge from NISC to fast is like application scale from like noisy intermediate scale. And so we started to see some of experiments. So we have seen a lot of experiments using these noisy devices already. But what we haven't seen until recently is experiments with these kind of like fault tolerant machines. These are machines that hopefully when scaled up we'll do magic. These are the ones that will do the magic. So experiments have been like catching up. So I would say stage one of fast, we could see this pretty soon, like in a couple of years. We will see a relatively big quantum computer that can do relatively non-trivial computation. So that is kind of within reach with current technology. Stage two is extremely different than stage one. Maybe like we're not even sure that the current devices will be the same devices or even like the same like another variant. Maybe we will end up with something totally different.
Right.
Not in spirit, of course, but just like in the
Right. Yeah.
hardware. How does it look like? Um, so yeah, the hope is, let's say, I would say in a decade that this happens. I mean, as like someone my age, if this happens within a decade, I'll be extremely happy myself. Uh, but yeah,
Excellent.
and I also want to say, like, I mean, so there is like a quote of von Neumann. They were like talking about what would be like the value of classical computers. They were like inventing that back in the last century, and they were like, so we don't know, like they couldn't forecast what will happen, and they said that probably the most transformative transformatives benefits that are the ones that we cannot predict right now
Right.
because they are the furthest of what we can imagine. So there is like a limitation of like imagination here, and with quantum, this limitation is even way bigger because that's like a completely different story we're like fidgeting with. So yeah, so it's hard to predict, but we know the potential. We know it's there.
It's funny because my next question was going to be, what impact do you see it having? And it sounds like your answer is we can't even imagine yet because once it's there, it's going to open up like whole new worlds.
Yes, I would say yes. But so like, let's. I know I need to focus on what we can predict, what we know with certainty, and I think I personally, even though it's not my field of work, which is quantum security or cryptography,
Right.
this is not my work, but I know that this has priority. So as you may know, that a quantum computer when they were first proposed one of their greatest initial expected potential that, oh, these can break the encryption that we're using
Yeah.
everywhere. And this has implications now that we know that this is kind of like viable, and that there is also global competition of some
Right.
sort. So it becomes a matter of I mean, absolutely important, or like national security, to have quantum proof security infrastructure. Not only, I mean, we said that like we know there is a gap, so that quantum computers are not there yet, and we can safely assume that this is the case in the US and anywhere. Like there is no one on earth that have this computer yet,
Right.
thankfully. Uh, but the process here goes like there is something that is called collect now, decrypt later. So
Hmm.
as someone who works in the government, I mean, many of your audience, especially like the more sensitive your job is, the more you should care about that. Um, collect now, decrypt later. So anything that happens on computers, on the internet right now, anything, I can collect the information that you're sharing from your computer to any computer. This doesn't mean that I can see what's happening, but I can see these packages. What I will have is a bunch of numbers, a bunch of crumbled information that I cannot, even with the most powerful computer right now, I cannot know what's in there. But what's happening is like people are collecting these, possibly, not to be paranoid about it, but possibly people are collecting these information, and they will be, maybe once I have a quantum computer, you can feed this info, and then you will know
Yeah.
what was being shared over this channel like a couple of years ago, or like few years ago. So again, I mean, the more sensitive your work is, what you're sharing is, the more like, I mean, you should be happy if, let's say, um, you see an upgrade in the security protocols, and then this is urgently, like hopefully within a couple of years at most, that we have quantum secure um, like protocols. So yeah, anyways, this may maybe deviated from the question a little bit, but I
Oh, no,
feel
but
like it
actually,
makes
no,
sense.
that's top of mind. I know in government, I know NIST has been working on those protocols, trying to get everyone ready. So,
Yes,
yeah,
that's
nothing,
absolutely important.
keep us all up at night for a while. All right.
Yes.
So final question, what do you want people to kind of take away from this discussion? If you were talking to someone at a cocktail party and they say, what's going on? What's the deal here? What do you want people to take away?
Okay. So quantum computers, they're like real. They're not science fiction-y anymore. The the US government is pouring a lot of money in this, and for a very good reason. And we should expect to see a ramp. The speed at which the progress will happen is not exactly linear. So there might be breakthroughs along the way, and hopefully in a gracious way, like we are ready. That's what we're saying, is like that these breakthrough, hopefully on our side, hopefully on the US side, and hopefully we are ready when that happens. So yeah, I mean, I would say any spending on quantum, I mean, of course, I would say that I'm working in that field, but any any spending on that is actually is very appreciated, is very necessary, and yeah, is like an is well justified. That's what I want to say.
Excellent.
So, yeah.
Excellent. All right. Well, sir, thank you so much. Really appreciate your time here today.
All right. Thank you again, John, for having me, and yeah, have a wonderful.
Unfortunately, we are out of time today. I want to thank our wonderful speakers for sharing their insights with us today. Just a quick reminder that we do have some great resources available for you to download, so make sure you check those out before you sign off. And like I said earlier, we will send you a link to the on-demand version of this training, so look in your inboxes for that. But on behalf of GovLoop, Dell Technologies, and FCN, I hope you enjoyed today's session. And as always, we really appreciate and value the work that you do. So thanks for taking the time out of your busy schedules to join us this afternoon. Have a great rest of your day, and we'll see you at our next training. Bye.